You're just using this to test it.
God, there's supposed to be 15. So basically,
Part of it is
10 of them. But I'm supposed to
for the
yeah, no kidding.
So do you guys have any questions? Any questions regarding the use of structures? Because that's going to be your last and final homework assignment. Oh, okay. I think it's taken very lightly. Okay. Are you guys ready? Yes? Kind of? Okay. How many people know what is a linked list in this class?
Linked list?
Linked list.
Jam.
Okay. You don't have to worry about the implementation because I will give you the code. So in today's class, I'm going to give you the code of a linear linked list. And we'll do the implementation of some of that stuff in assembly. I'll give you the C code first, and then we'll do some of that stuff in assembly. So don't worry if you have not taken cisp310 yet, because we are not going to talk about the algorithm. You will not be tested on the algorithms. I will give you the source code. We just have to do it in assembly. Okay? Yeah. Just. All right. So we'll go ahead and start with the structure. So we'll go to today's class, which is 0501. And we'll go with node.h. So this is all defined in C. There's nothing in assembly at this point. So I'm going to take this project from C to assembly step by step, the whole every single step along the way. So this will serve as an example of how you can do your next homework assignment. I do not have it up on Moodle yet, but that's going to be similar to something like this. So we have struct node, okay, and we'll define it like this. Inside the node, we'll have struct node next pointer, and inside the node, we can just store a particular integer. It doesn't matter what we are storing. The whole point is inside a struct node, it has a pointer to the next item. Okay. Are there any questions about this particular structure definition? No questions? Now, when I saw something like this the first time, in my mind, the biggest block was, how is this possible? Because we are still defining node when we see, struct node asterisk, p next. How is that possible? Well, as it turns out, it's really easy because every pointer, including a pointer to a struct node, is only 4 bytes. So it's okay if you do not know yet, how big the structure is, because a pointer to this thing is always guaranteed to be 4 bytes in a 32-bit system. So that's why, this is fine. There's no problem with this definition. Okay. So the next thing we want to do is to create the helper applications. One application so that we can export the offsets of these things. And I still haven't figured out how to use offsets, so I'm going to do it the old-fashioned way. So we'll have another program called print node offset, and we'll make it a C program. The first thing it will do is to pound include stdio, so I can use printf, and it will also pound include node.h because it defines the structure. Inside this program is a fairly simple main program. It does pretty much the same thing as what we described last time. All it wants to do is to print the offset from the beginning of a struct node to to each individual member. So in this case, we have node, which is the name of the structure, underscore. I use underscore to separate the name of the structure from the member that we are dealing with at this point. P next is the name of the member. And we're just defining this to be an unsigned integer. And the way we do this calculation is just like what we talked about last time. We have to cast the address of a particular node. So we'll say struct node n, so that we have something to talk about. So we'll say the address of n.p next is casted to a character pointer, and then we'll go ahead and subtract from this the address of n itself, the beginning of the entire structure. And then we'll do the same thing with the member called I, which is the only content inside the node in this case. And we also want to know what is the size of it, because in case we want to copy a struct node, or we want to pass a struct node by value, we need to know how big that thing is. So we say node size, and that's easier to do because we can just say size of, and that's all we need to do with this particular program. Any questions at this point? If there are no questions, I'm going to borrow the makefile from last time. And I first have to find where the makefile is. So I'm going to say that was from the 24th of April. Okay, so that's it. And then we'll just copy it to today's folder. And then we'll make some minor adjustments, because it has pretty much the entire structure there already. We just have to make some minor adjustments. Okay. And I cannot remember the name I'm using this time. So let's change to today's folder first. Okay, we have print node offset as the name of the executable. So we have print node offset, and use the same name as the source name. There we go. And we kind of have to decide, how we want to call the other, program. So we'll say linked list .c, and then the executable we just call it linked list. And at this point we don't have any assembly file, and we'll go ahead and create linked list.c. Pound include stdio. Pound include node.h. Yep.
Do you need to change your include file as you want now for assembly? Your assembly include file?
Well, I'm not done yet. Oh, you mean the name? Yes, we have to make changes to that also. But I just want to have a stub at this point, so that the makefile does not complain about it. But you made a good point. We have to go ahead and change the name of the include file. So we'll say this is struct node.inc. It depends on print node offset. That. And I think the rest should be okay. And everything seems to work. We can also make that particular file, explicitly, and make sure that when we run that program, it prints out, something that's sensible. Are we doing okay so far? Okay, but the first thing we want to test is, is the makefile really working? If I make changes to node.h, is it going to trigger the recompilation of print node offset? So we want to make some, we want to double check things, along the way, so that we don't have a big pile of stuff that is unknown, and then when we try to say make, things do not work anymore. So touch node.h, and then we remake print node offset. Make print node offset, and it does trigger the recompilation, which is correct. So we do have all these pieces in place at this point. Are we doing okay so far with this? Okay. The first thing we want to do, we'll start with something simple. We'll start with a subroutine that initializes a node where the content I is 0 and the pointer is also 0. So we'll start with something that is relatively easy. So we'll go with We'll do it in C first. So we'll start with void init node, and it takes a struct node pointer. And all we want to do in this case, well, let's make it slightly more complicated. Okay, with a with a parameter. Okay, so I mean, we do want to know, how to use the pointer as opposed to how to use a parameter that is passed by value versus passed by reference. In this case, we have p node, p next gets null, which is just 0 itself, and then we have p node I gets parameter I. So let's make this our first subroutine to check. First of all, we have to make sure that this is working in C first, and that's not too bad. We can say struct node n, and because all we want to do is to double check on this one, we can use GDB for that purpose. So we'll go ahead and say init node, the address of n, and we want to initialize the member I to say 23. Return 0, and that's my program at this point. Any questions about this program at this point? Are there any questions about the subroutine itself? Is everybody familiar with line 7 and line 8 and what these two lines should do? Is that okay? So everybody feels comfortable with the arrow operator? Now, there are other ways to do the same thing. In other words, if I do not want to use this particular syntax, I can actually change the syntax to something like this, because p node dereferenced is a struct node. Now, with any struct node, you can access member p next using a dot. So these two lines, line 7 and line 8, actually mean exactly the same thing. It's just that we prefer the pointer operator because it seems to imply the pointing effect better than a dot notation. If you come from a Java background, then it's a dot all the time. Is that okay so far? Does everybody understand how line 7 and line 8 really mean the same thing? It's okay? All right. So we'll go ahead and just test this program the way it is written, all in C. And we'll say make, and then GDB linked list. That we'll put a breakpoint on line 16, run the program. By the time we get to line 16, struct node n should be initialized. So we'll go ahead and say print n, and it prints out the entire structure, and everything is correct because the null pointer is nothing more than 0 itself, and we have 23 as member I, and that's exactly how it should be initialized. Any questions? So we'll go ahead and try to implement this subroutine in assembly first. But before we do that, we'll go to the C file and then make a prototype out of this, and then we'll use pound if 0 to comment this code out. And then we go from line 7. Oh, somebody told me how to select a block of code. Capital
Capital E.
D.
V for Victor.
Victor. Okay.
What's your vector, Victor? Roger, Roger.
Okay, so we'll have init no dot uppercase s.
Oh, I need clearance, or I need clearance.
Paste it.
What?
Now, you have to be careful when you comment out C code when the extension of the file is dot uppercase s instead of dot lowercase s. Dot uppercase s means GCC will feed this file through the C preprocessor. So if you have a single pound sign and you have, well, in this case we don't have any if, but if you do have if inside the code, then it becomes pound if, and the preprocessor will interpret that, and then it's not going to, the C preprocessor will feed the wrong stuff to the assembler, and then the assembler will not be able to work correctly. When you have two pound signs, then the pound itself is escaped, so it's not going to do the interpretation like it would without the double pound sign. And here we have pound include, how did I call it? Struct node.inc, struct node.c, and then we'll go ahead and define the subroutine. Dot global init node dot text init node, and guess what? I'm just going to test it like this, just to make sure that the make file is going to handle this just fine. Now, what do you think? I don't think the make file is ready for this yet because I have not defined the assembly source file in the make file. So when you do a make at this point, it's going to complain and say init node is not defined because init node dot uppercase s is not yet specified as a source file inside the make file. So as you implement programs like this, you have to make changes to the make file. Otherwise, you end up with minor problems like these. So in the make file now, I have to include init node dot uppercase s as a source file. Make again, and it's complaining struct node.inc no such file or directory. Oh, that's because I forgot to include that into the make file. So now it will also take the assembly file to generate the dependencies. Linked list.c line 5 missing separator. Okay to me.
Yeah, that's fine.
The pound if 0 is blocking out this entire code. And missing separator.
Check the make file itself.
Copy the line without tab.
Hmm?
Oh, yeah, there's no tabs. There's not a proper tab in the make file.
Sorry?
So there's not a proper tabs in the make file because the missing separator comes from that.
Because you made a copy of the line. It's just smaller than.
The line that made a copy of or the includes is not here. That's a tab. Okay. The other way to do it is just to do a GCC by hand first, just to make sure that I didn't make a mistake like that. And that worked just fine. Okay, it's actually complaining about list.c. Okay. Clean.
Yeah, it's in the makes.
It's in the make file itself. Oh, I know why. It's including the source file itself, I think.
I'm going to say ASM source right
Yep,
now.
there we go.
You already have ASM source though, yeah.
Hmm?
You have that 2 lines below.
Oh, yeah. You don't need that line at all.
Oh, because I have that. Okay, it's not finding struct node and it doesn't understand how to generate struct node.inc. Struct node.inc is listed here. It's not making the association. And that's a tab. And it knows how to do that. Okay. Doesn't know how to generate it the first time. It's a cyclic kind of thing because the first time, the Yeah, I think it should be fine now. All right, so we'll go ahead and test it again, just to make sure that this is working the way it's supposed to. So we say GDB linked list, and we want to list from linked list.c itself. That's the init node. Where's the C program? Okay, this is the C program. It is linked. It is compiled with -g, and then the linker is not linking with -g, but I don't think that's necessary. Let's see. There we go. It's because I ran gcc-c manually, and it picked up from the manual run of GCC. So the object file from that manual run of GCC did not include the debug information. So when I ran this with GDB, GDB could not pick up the debug information either. So everything works except the subroutine actually doesn't do anything, but the linker works, the makefile works. So now we can go ahead and try to populate the actual subroutine. Are we still doing okay? I mean, have I lost anyone yet? Nope. Okay. So we'll go ahead and change this file and actually implement the subroutine. And so we'll go ahead and move things around a little bit so that the C code and the assembly code are interleaved. Now this part is optional. You don't have to do it this way, but I always do it like this, because it is, it's just easier for myself to remember how all these different things relate to each other. What is the next item?
Return value address.
It's returning void. I don't think void needs a return value
You
address.
need it, trust me.
What is the next one?
Don't you need your dot text above all that stuff?
Say again?
Don't you need your dot text above all that?
Yeah.
Yes, does that matter?
It's already in dot text to begin with, so it's not going to notice any difference.
Oh, so it's just like.
By default, it's dot text. You have to use dot data to switch to dot data. So it's not really going to hurt, but it doesn't hurt to remember to put it up at the top. Okay, but what is the next item? We have ODBP, and then we have the return address. We're traveling back in time because the higher the address in the stack, the earlier it was pushed on the stack. So what is before that? One of the two parameters, right? But which one has the lower address? P-node. P-node has the lower address because the first parameter has the lowest address. And that's because the parameters are pushed in reverse order. The last parameter is pushed first, and therefore it has the highest address. So P-node is return address plus 4, and that's because return address is a 4-byte thing. And then we have I, which is P-node plus 4, and that's because P-node is a 4-byte thing. It is an address. It's a 32-bit address. We do not have any local variables, so we don't have to worry about the definition of local variables. The dot global really can go anywhere. It doesn't really matter. It can go as the last line. It will still work correctly. But as a convention, let's just put it up at the top so that we keep things consistent this way. Okay, now we have to implement this particular line. How do we do it? Well, first of all, let me just ask you this question. If I use a move long instruction and I'm moving P-node paren EBP to EAX, what is EAX after this instruction? The question is EAX the first 4 bytes of the node structure that P-node is supposed to point to, or is EAX really just a pointer to a struct node? It's a pointer to a struct node. In other words, EAX is the same as the C parameter P-node at this point. Okay. So we'll say EAX is P-node. It points to a struct node item. Is that making any sense? Now, it really helps to comment each and every line, especially when you are writing the code, because you really want to keep track of what is in this register at any particular time. Okay. Next line is, well, we are almost done. I mean, we can finish this entire statement in one single line here. Okay, let's deal with the right-hand side first. The right-hand side. Null is really just 0. Okay, 0 can assume any type, including the type of any pointer. So null is the same as a 0. What about the other side? How can I put something into the p next member of a structure that is currently pointed to by EAX? Okay, think about EAX. EAX is a pointer already. It points to the first byte of a struct node. Okay? But we don't want to store something just to the beginning of a struct node. We want to store something to the member called p next of a struct node. Remember all the definitions that we dealt with earlier from print node offset? How do we use some of those things? Do we have a symbol that represents the number of bytes as an offset from the beginning of a struct node to p next as a member of a struct node?
Yes.
And that starts with the name of the structure itself, followed by the name of the member. So what if I do something like that? That would do it. Okay? Because EAX at this point is already pointing to the beginning of the entire structure. I don't necessarily want to copy something to the beginning of the entire structure. I want to copy to a particular member of the structure. The symbol node underscore p next is the displacement from the beginning of the struct node to the member called p next. So that's the last piece of information that I need to finish the copying. This copies 0 to member p next of whatever EAX points to. Are we doing okay so far?
Where is that node underscore p next? I saw you do print f on that, but I guess I missed where you
It's in
actually made that.
struct node.inc.
Okay.
And that's generated by print struct node as a program. Okay, at this point, somebody's going to point out and say, but Tag, you are just taking this whole class through the park for no particular reason, because look at that. Node underscore p next is defined to be 0, so why do we even bother to include that in this instruction here? Because we could have just just specified indirect EAX and it would have done exactly the same way, right? But you know how I am, right? Because when I grade your homework assignment, I would do nasty things like go to node.h and go, let me just change the order of the members. So any program that make the assumption that a particular member is the first one and therefore we do not need to use the symbol name for the displacement is going to be broken because simply because I changed the order of the definition of the members. So that's why it's always a good idea to use the symbolic names and not to use numbers. If you use 4 or 0 or anything like that, it would be just as brittle, because if I change the order here, then your code will not be updated automatically. But Tag, I don't believe you. Even if I do something like that, there's no way the assembly program can be updated automatically and be insensitive to the ordering of the definition of the members. Well, we'll take a look at make at this point. I just made a change to node.h. I flipped the order of the two members. What happened here is make automatically figure out the dependency, and this one is obvious because linked list.c as a C program has a pound include node.h. So if I change node.h, it should recompile itself. Same thing goes for print node offset.c, which is a pure C program, and it also has pound include node.h. So that makes sense. But see what happens next though. the next thing it does is it doesn't give me the executable linked list. It first gives me the executable called print node offset. That's the first thing that it did. And then right away, it uses that executable in order to recreate or update struct node.inc. So at this point, struct node.inc itself is updated. It has a newer date, and it is also refreshed to reflect node.h. As a result of that, now it is time to reassemble init node.s, uppercase s, because that file pound includes struct node.inc, the include file. So once this is all done, then the last step is really just to link everything together so that we can have the executable called the linked list. So this part, up to here in about half an hour, this is the workflow. I mean, this is how you want to structure your next homework assignment, is to so that you have a setup in the makefile and also the executable called print node offset, so that if you make any changes to the C definition of the structure, the rest of your program will automatically update. Yep.
That includes your definitions at the beginning of your assembly file?
That includes?
Well, if you switch the order of the struct, wouldn't it change the position of the parameters, or does that, it just
No, the
depends on how it's
parameters
called?
will not switch because the parameter is a pointer to a struct node.
Okay.
So that positioning is not going to change because it's still the same.
Okay.
Yep. But you can see that struct node.inc is now changed because p next is no longer the first member; it is now the second member.
Dang. That's pretty good. Now if I can just do that on my own.
Well, YouTube has a pause button.
What's that?
YouTube has a pause button.
Oh, that's true.
Well, you pause buttons?
Hmm?
Yeah. Does the test have a pause button too?
Does the test have a pause button? No.
We should make that happen for next.
I don't know how you can do a time dilation, during the test.
Do you want us to know how to make or do the crazy way that you do make files for the test?
For the test, it's going to be all concepts, and I'm very tempted to make it all multiple choice.
Okay.
But in the past, I have people complaining to me that my multiple choice tests are harder than my practical tests. I don't know why. I mean, having all of the above and none of the above, as options, didn't seem to help.
Yeah, but still, probability-wise, you can still guess and have a better chance than putting nothing in.
Well, when I have multiple choice questions, I also have the balancing thing, which means if you on the average have 5 choices per question, the wrong answer will get you a quarter point deducted. Just like SAT and all.
So in other words, if you get it all wrong, you get 0 points.
Sweet.
No. If you get it all wrong, you get a negative score.
Well, right, but I mean, if in general you were to get it all wrong
What if it's
on it
blank?
instead of getting partial credit, you get no.
What if it's blank?
Old style.
If it's blank, it's just 0. Okay, so at this point, I think I should explain why there's a quarter point deduction. Does anyone not know why there's a quarter point deduction when there are 5 choices and this is all multiple choice?
What?
Okay, have you guys taken the SAT or some other public exams where if you answered incorrectly, there will be a deduction of points? If you do not answer at all, it's just a flat 0. But if you answer incorrectly, they will deduct a point, or a fraction of a point. So in general, if you have 5 choices and you just randomly guess the answer, what are your chances of guessing something that's correct? 1 in 5, right? So the chances that you get something wrong is 4 in 5. So what the quarter point deduction is supposed to do is over a lot of questions, the average of someone who has no knowledge whatsoever of the subject matter should get a 0. They can guess randomly, but in the end they will just get a 0, not a negative score, not a positive score, because the number of correct answers or number of answers that are guessed correctly will be 1/5, but the number of answers that are guessed incorrectly will be 4 times as many. So if the if the score of the wrong answers is 1/4 of a point, it will just balance out the points that person gets just by luck.
Except when the test is really short, and then you do actually average negative score then. It will, yeah.
And some people are particularly lucky, and some people are particularly unlucky. But that's the thing about multiple choice is, that's there's a deduction for wrong answers.
So does that mean with the make file stuff, where you
Yes, you have to.
With multiple choice test questions, I think I can expand the type of questions a little bit, because it's all multiple choice. I mean, you have 5 choices, and so you don't have to memorize as much, I mean, in theory, you just plug in each particular choice and say, okay, is this going to work? Is this going to work? Is this going to work?
We
Is
get to
this
bring
going to
our
work?
computer then?
Hmm?
We get to bring our computer then.
Yeah, you can bring a Turing machine. You guys will like that class. At some point, you will see, you will take a class. It's called computational theory, and they will first introduce the first machine is called, FSM, and FSM does not stand for the flying spaghetti monster. It stands for the finite state machine. I always got those two confused. They both seem to do the same thing. So the first one is a finite state machine, which doesn't really do a whole lot, but it already does enough, that is related to what we have, what some of us have done already. Is anyone familiar with what is a regular expression? Some of us, okay? A regular expression is a generalized search criteria, okay? That's one way to describe it. But a finite state machine is basically, quote unquote, a machine. Okay, any regular expression can be translated to a finite state machine. So any regular expression that can be recognized by a computer, by VI or some other tools, you can actually construct a finite state machine to do the same thing. But finite state machines has limitations. It cannot do anything that is nested. If you want to deal with anything that's nested, such as a C program and many other programming languages that can be nested, you need what we call a stack machine. So you need to have the concept of a stack on top of the finite state machine. But if you want to go beyond that, there's also called a type of machine called the Turing machine, and that's the most general theoretical machine that exists. And even with Turing machines, you can actually construct problems that cannot be solved by Turing machines. Anyway, just a preview of computational theory. And some of you will really enjoy that class. If you like cisp310 and you yearn for more, computational theory is going to be a fun class. If you really hate cisp310, despite Mr. Fox, Professor Fox being a very good professor, you're going to hate. You're going to hate computational theory, because guess what? It's all math, and it's all math that you haven't seen before. But it has similar things, okay? Mappings, functions, and stuff like that. Anyway, enough digression. All right.
Oh boy, I hope the pay's worth it.
Well, I mean, people are making upwards of $80,000, coming out of Berkeley as an undergraduate. So I think it's worth it.
So it's worth it.
Yeah, I think so.
Okay,
All right.
stick with it.
But wait, so why am I teaching here? That's a different story. Okay, so are there any questions about setting up the infrastructure of a program like this? Okay, at this point, I haven't really implemented a lot of useful stuff. It's a very simple function, but I make sure that my make file is working, and it's updating the include file automatically. So that's an important step of your homework assignment. All right, so once we have this done, we can go ahead and do some more fun stuff. So we go back to linked list.c, and we'll find out what else we can do with the linked list. What do you think the name linked list come from? What else can you do with a linked list? Well, you can create a little chain of these items where one item can point to the next one, and so on and so forth, right? So we'll go ahead and we'll implement something along that line. So we'll go ahead and implement insert node to list. Okay. Struct node. That's my list. It's not a typo. It is a double asterisk. And then we have struct node. Okay. So what we want to do is we're inserting one item at the beginning of a linked list. So this is basically, this linked list behave more or less like a stack. When you're inserting, you're always inserting at one end, but you're also using the same end to remove items. So the order of inserting and removing is really the same as LIFO, L-I-F-O, last in, first out, which is also what a stack does. So when you insert an item like this, you don't have to worry too much about the data structure part. That's in cisp310. So you just have to focus on the C statements so that you can actually understand and figure out how to do it in assembly. So the first thing we want to do is to make p node, p next. We want it to point to whatever p list is pointing at this point. So we have that. And then after that, we'll say p list, or whatever p list points to gets p node. And that's how we insert any particular item at the beginning of a linked list. Yep.
What's the double asterisk?
Which one?
The double asterisk?
The double asterisk means p list points to, okay, one way to look at it is p list is the address of a pointer to a struct node.
Okay, so like nesting point.
It means it's got to go to two locations to get the information there to the point.
It is the address of a pointer to a struct node. So the objective of insert node to list is to change whatever p list is pointing at. And that's why all the access to p list they're all dereferenced. Okay. Any questions about this one?
Yes.
Go ahead.
Can you help me visualize this particular
Yes.
function, please?
Yes, I can help you visualize, but it's not going to be easy to draw it, in a way that I can capture on screen.
Okay. Well,
So
you can
somebody
just
needs
draw it on
to
the
take a
board.
picture.
Yeah.
Yep. Cell phones. I mean, we probably have. How many students do we have in class? About 40. So I would say that we have about 60 devices that can take pictures in this class. Hey, somebody's gonna have a Wii, not a Wii, a DS. Okay, somebody's gonna have a DS here, and then you don't have to hide your DS. I understand. There was one time I was teaching cisp310, the class before the C class, and there was a whole row of students at the back of the classroom, and every single class, they just played, networked games, during the class time, and well, let's just say that the grade reflected that. Okay, so getting back to this, let me just go ahead and do something to make use of this. Okay, so at this point, I'm going to change the structure of the program just a little bit, so that we'll do something like this. We'll say pn gets malloc size of node like that, and then we'll do an initialization. Init node pn and say 23. And then we'll also have struct node. And this is our list. So we'll make this one the first item in the list. But before we do that, we have to okay, this is not done yet because we have to check whether p list itself. No, p list cannot be. Oh, never mind.
Don't error check.
Nope, no need to error check it. List starts with a null, okay, and then we'll say insert node to list, pn to the address of list. Was it the other way around? I think it's the other way around. The address of list, and then we have pn. Just double check. Yep. All right, so we'll just write the program with one single node to make sure that that one single node is attached correctly before we move on to have two nodes. Any questions about this program? If you guys want a visualization, I can attempt. Okay, this is what I'll do. Yep, go ahead.
I was going to say, did you include standard lib?
Sorry?
Did you include standard lib.html?
Yeah, that's just a warning. I know what I'm doing.
Yeah, okay.
Says the man who says it. I know what I'm doing, right?
Focusing on compiling.
The famous quote is, trust me, I know what I'm doing, and that comes from Sledgehammer, from a show of the same name. How many people know what is Sledgehammer? Okay, that's the younger people probably don't know about that show. They had to pull it off the air because of Rodney King, I think. That was the reason why they had to pull it off the air. It was because of police brutality, and Sledgehammer as the character, always displays excessive force. Let's just say. All right.
He's got a dash.
Sorry?
Just add that dash lowercase w everywhere. Tells GC to ignore all errors. And you tell it what you're doing.
Oh. Okay, we have error on line 29 and line 5.
Just ignore all that, that's fine.
Should do that on my test.
Yeah.
Just ignore all warnings.
You will accept this works.
Oh, I forgot one asterisk here, but that's not a problem. That's not why it's complaining. Maybe it is. It is. Okay, there we go. All right, so we'll use GDB again because the program really doesn't do anything that is visible from the outside, so we have to use GDB to look at the program. Okay, we'll put a breakpoint after line 27. We'll put a breakpoint on line 28. We run the program, and we have a segmentation fault from line 27 because PN is okay. So here's the next question. Your program crashes like mine, and what are you going to do? Look up tax email address. Nope. So what are you going to do? I mean, this is actually pretty easy because the program crashes, but letting you know where it crashed. In other words, you're not over at La La Land yet. Okay, you're still somewhere within your program. And if you look at the instruction like this one, which operand do you think is responsible for the segmentation fault? Can the first operand be responsible? No, it has to be the second operand. When you look at the second operand, what is your next step? What are you going to display, to say, okay, why is this program crashing? I'm going to look into blah, blah, blah. What is that? The value of EAX. All right, that makes sense. So we'll go ahead and say IR EAX. Oh, it's a 1. Okay, no wonder. Okay. So that means, when you debug a program like this, you have to go back to line 27 because you have to make sure that when you pass PN to the subroutine, that PN is a valid pointer at that point. So we'll put a breakpoint there, start the program from the beginning, and it's not stopped. Oh, okay, I have to say B linked list.c:27, and that's something that you also will have to do because you have to not only say which line you want to put a breakpoint on, you have to say which line of which file because you will have multiple source files. Okay. Any questions? Questions? start the program again. This time we're stopping at the right point. Print pn. And pn is actually correct. There's nothing wrong with pn. So when the program doesn't behave correctly, it has to be in the subroutine itself. And we already know what is the problem, right? Don't we? Okay, let's take a look at the program, and you guys tell me what is wrong or what is missing in that program. Hint, I created a whole bunch of symbols, but the symbols only make sense if the call frame is set up in a certain way. So when we look at the source file, you tell me whether the call frame is set up correctly or not. This is the program. What is old EBP again? As a symbol. What is that telling me?
Telling you where the frame pointer is going for the
It tells me that EBP should be pointing to its own old value. Look at this program here. Do you think EBP is pointing to its own old value? Do you think EBP itself, is an effective frame pointer for this particular subroutine?
No.
Nope. So that's it. All right. So we are forgetting to do something important, which is the entry point and the exit code. So the entry code is what? Push L EBP, because we have to save EBP. That means before we return, we also have to remember to pop EBP. After push EBP, what else do we need to do? Move L, E, SP to EBP. In other words, EBP is a snapshot of the stack pointer, so that we can refer to EBP all the time. Even if we continue to push and pop and change the stack pointer, EBP does not change. But that also tells me that in the end, at the end of this subroutine, we should probably do the same thing here, even though it is not required. Okay? Move EBP to ESP is actually not required in this case, because in the actual subroutine, I did not make any changes to ESP whatsoever. In other words, after move ESP to EBP, those two registers remain exactly the same throughout the entire subroutine, which also means this particular instruction is technically not required. But I always put it there anyway, just in case I have local variables, or for some reason I did not balance the stack correctly with pushing and popping. This will save the day. It will make faulty programs appear to be correct.
So it's a catch-all.
It will catch most problems with an unbalanced stack. The only type of unbalanced stack it cannot really save is you have more pops than you have push. Then you will be starting to destroy the content of the stack in that case. Potentially you'll be destroying the content of the stack. But if you have more push than pops, then you're just wasting space on the stack. This will recover the stack pointer to the right place before pop EBP. Okay. Any questions about this? I'm not only showing you, how to set up the program, but also, basically debugging techniques. How do you approach the problem? Your program crashes. What do you do next? Scream and run like a chicken without its head. That just reminds me of a certain scene from a Chicken Run. That's way, way, way over. All right, so let's try it again. GDB, linked list. Put a breakpoint on, well, let's be brave and put a breakpoint on line 28. Run the program, print pn, and print what pn points to. And it is incorrect because I forgot the second instruction. Because I only translated one, the other one is not translated yet. Right? Yeah, there we go. But this is the kind of thing you have to do also when you're debugging your program, because sometimes we just forget to finish the entire subroutine before we test it, and that's what happens. Okay, how do we do this one? We are taking parameter I, and then we want to copy the value of parameter I to member I of whatever p node points to. Now we can reuse EAX in this case because EAX is already initialized to be the same as p node, so we can just reuse EAX. So you have several options here. The most straightforward option is really just move L, in this case I EBP, which is parameter I in this case, to another register. I would use EDX and not EBX because you are responsible to save and restore EBX because the caller assumes EBX does not change. But EDX, is fair game, so it's okay to basically clobber the value of EDX. Once I have I, parameter I in EDX, the next step is really kind of the same as before. We move EDX to, in this case, node underscore I EAX, because EAX is still a pointer, so it should still be fine. Yep.
Why do we have to move it into a register first?
Because you cannot have two memory operands. In other words, I cannot change this instruction to I EBP, even though that's what I want to do, but I can't do it because now I have two memory operands. You can only have up to one memory operand with move, add, and most of the other instructions. So that's why I have to change it to EDX in this case. All right. So save it, make GDB again. Put a breakpoint on line 28. Then line 28 again. Run the program, print whatever PN points to, and this time we got everything. Okay. Any questions? No questions? Yep.
When's the final?
When is the final?
It's 2 weeks from today at 7:45.
It's 8 o'clock.
Or is it 8 o'clock?
Yeah, 8 to 10.
Oh, that's 7:45 is when our previous class is.
Yeah. So make sure you have a good dinner, but not too full, because otherwise you doze off, and that would not be
Weeks from
good.
today, starting at 8 o'clock to 10.
Yep. All right. Okay, now that this is done, let's go ahead and finish the entire program and make sure the linked list is going to point to the first node. Okay. So we'll single step, go into insert node to list. Okay, now this part is kind of important because what you want to do is to print list first. List itself is a pointer, and that pointer is a null pointer at this point. Are we doing okay so far? The other thing you want to do is to print what is the address of list, because you want to remember this number so that you can identify this as one of the parameters to the subroutine. Are we still doing okay so far with this? Okay. So now we can single step into the subroutine. When you're in the subroutine, you want to print plist, because now you want to say, oh, so the address of list becomes the parameter called plist. Okay. So now that you know plist is really the address of list, what is this part saying? Or what should be the value of the right-hand side of this assignment? It should be 0. Okay, it should be 0. Sorry. Okay, it should be 0 because list itself from main has a value of 0 because it's a null pointer. The address of list is this particular value, which also means if you dereference this particular address, you should get 0 back. And that's what we are doing on the right-hand side of the assignment. We are dereferencing this particular address, we should get 0 back. And what we are doing is storing that to the p next member of whatever p node is pointing at. So we single step through this, and then we single step through this one here. And after this step, what do you think list becomes in the main program? I'm going back to the main program at this point. What do you expect to see when I say print list? How does list relate to pn? Pn is a pointer, or is an address of a structure that I allocated by malloc. So what do you think list should be at this point? List should be pointing to the same place because list is pointing to the first node of the entire list. How many nodes do we have? One single node. So this has to be the same thing. So you can confirm that by saying print list, and they are in fact the same. Are we still doing okay so far? This is a linked list with one single item, so we want to test the program with 2 items now. So with 2 items, I can do pretty much the same thing. I will just go ahead and copy these 2 lines, and copy this 1 more line. Does anyone want me to explain what malloc does? Memory allocation? Okay, it's the same thing as new in Java. Okay, it's allocating. It's a very crude way of doing allocation because you have to tell malloc exactly how many bytes you want to allocate from the heap. And the casting here is necessary because malloc is supposed to return a void pointer, and you cannot assign a void pointer to a struct pointer, so you have to do a type casting here to make the C compiler happy. You're convincing the C compiler that you know what you're doing. The C compiler says, I can assign a pointer to any pointer. That's fine because they're all 4 bytes. But it wants to make sure that you know the type of the pointers before you can do the assignment, to make sure that you're not assigning a pointer of the wrong type to the other type. All right. So if I change this one to say 11, then I will have 2 nodes. The question now is, what do you think those 2 nodes? How do they relate to each other? And which one do you think list will point to first? So we'll go ahead and make the program again. GDB link list, and we'll put a breakpoint on. Let's see. We'll put a breakpoint on line 33 in this case, and the program is now done. So what do you think list is pointing to?
Second node.
It's the second one that we allocated, which is the last one that we added to the list. Okay. And so the only way, or the easy way to confirm that is we look at what list points to, and it is 11, the one with an address of 11. So what do you think this is the address of?
The first node.
The first node with I equal to 23. Well, we can double check that. We can say print dereference list points to P next. And sure enough, that's our first node, the one that has a value of 23. So that's why I said a linked list like this, a singly linked list, almost is like a stack because it is last in, first out. Are we doing okay so far with this? Okay. Now that this is okay, the C code is working, we'll try to implement it in assembly. So this is what you need to do with your homework assignment 2, is you want to run the program in its C form. Every single subroutine that you want to implement in assembly, run the program in C code and make sure that you understand the C code line by line, which pointer is pointing where, and so on and so forth, before you try to implement it in assembly. Because the worst thing you can do is not knowing what the C code actually means and try to implement it, because there's no way you can test your assembly code in that case. Okay, you got to make sure that you know the reference points, so when you test your assembly code, you know what they're supposed to do, so that you can say, oh, okay, I know there's a deviation here. The C code is doing this. My assembly code is doing this. Something is wrong. I have to stop and check at this point. Okay. All right. So getting back to the C code, now we have to implement insert node to list in assembly. We comment it out, take the first line, turn it into a prototype to make the C compiler happy. So now we can do a shift B, yank, save this file, and create a new file called insert node to list.uppercase S. And do exactly the same thing as last time. Include, I think it's called struct node.inc .text.global, and the name is insert node to list. Okay. We have our entry point here, insert node to list. And this time, I remember, push out EBP, move ESP to EBP. At the end, we have the reverse. We have move EBP to ESP, pop EBP, and return. Okay. And just like last time, I'm going to start with the usual stuff. Old EBP gets 0. Return address is old EBP plus 4. Obviously, you can just copy and paste it from your other program, but it doesn't really take that much time to retype it. And then we have p node equals p list plus 4. All right, so now we have all the offsets to all the parameters done. And how do we implement this? Well, the first question is what do we get when we dereference plist? Do we get a struct node or do we get a pointer to a struct node? That's the question. We get a pointer to a struct node. And we can store that in a register because it's only 32-bit. It's an address. Okay. So that's our parameter. Okay. Every time I refer to a parameter, I always have to make sure that I use EBP with that label. Is that making any sense? plist is the name of a parameter. It only works with EBP. Okay. And as usual, I will copy that to EAX. So that means EAX is plist. It is a it's an address of a pointer. Okay, I wouldn't call that a pointer to a pointer because its function is really the address of a pointer, even though it is still a double asterisk. It's just how you want to call it, and how you call this can make a change, can make a difference, making it easier to understand. Okay, next line is what do we do next? Do I have the right-hand side of the assignment operation now? Or do we just have one part of the right-hand side? We need one more step to get to the actual right-hand side. But EAX is plist, but the right-hand side is not plist. It is the dereference of plist. So we need one more statement to get to the right-hand side. Dereference it. Yeah. So we can say move L, EAX. Well, there are two ways to do this. I'm just going to be lazy here and kill two birds with one stone. What am I doing here? Why do I say that I'm killing two birds with one stone? Well, first of all, there's a dereference, okay? Because I am using the indirect operation or the indirect operand to dereference EAX. So what I'm pushing on the stack is not EAX. What I'm pushing on the stack is what EAX points to. And that turns out to be the right-hand side of the assignment operation. I'm putting this on the stack so that I can free up EAX, I can reuse EAX, and I don't have to worry about having to use another register at this point. Yep.
Isn't that two memory operations?
That is two memory operation, but it is allowed.
Special.
It's a stack operation, so it is allowed.
It's very special.
It's a CISC, special thing, because with a RISC processor, the only thing you can push on the stack is a register. So with a RISC processor, I would not be able to kill two birds with one stone. It's always just one thing at a time. But with a CISC instruction set, I can do something like this, which comes in handy sometimes, like in this situation. If I don't want to do it this way, I can always do it the slightly longer way, which is move L EAX to EAX, dereference it once, and then push it on the stack. So it does the same thing. Okay, now that the right-hand side is on the stack, I can focus on the left-hand side. The left-hand side is something that we have seen before. So in other words, whatever we did before to get to the left-hand side will still work in this case. So move L, P node, EBP to EAX. And I should write some comments here and say EAX is P node at this point because it was something else. So if I don't write a note here, then I will still read my comment from earlier and say, oh, it's plist, but it's really not plist anymore. Okay. And once again, I can kill two birds with one stone right now because I can use a single pop instruction to pop it into the dereference portion, or I can pop it into the p next member of whatever p node points to. So I'll use that instruction first, and then use a longer sequence of instruction as a second step. So now I can say, okay, the short instruction is node underscore p next EAX. That completes the instruction. Okay, let's think about what we are doing here. It's a pop instruction, which means there's an implicit operand, because there has to be a source, right? What am I putting into this operand here? Well, it's whatever we pushed on the stack earlier. What did I just push on the stack with the push L instruction? The right-hand side of the assignment, okay? So, which is the right thing already. So I'm popping the right-hand side of the assignment to whatever EAX points to, but not quite exactly there, with a displacement of node underscore p next. In other words, EAX is a p node. It is pointing to a struct node. I do not want to copy or pop into the first 4 bytes of a p node. I want to pop into the p next member of a struct node. So this will kill 2 birds with 1 stone. But in case someone do not want to do it like this, we can always do it in the long way. The long way to do this is pop L EAX, which also defeats the whole purpose of using the stack, because now using the stack really doesn't buy you anything. So when you pop you have to pop it into a different register.
Because otherwise you're going to wipe out.
Yep. You pop it into, say, EDX, and then now you can say move L EDX to node underscore p next in based. This is the based operand EAX, like that. So that's the longer way of doing the same thing. Now, if you're doing this, if you're doing everything the long way and just using all the registers, you might as well save all the time from pushing and popping, and change this one to EDX. So quite a few different ways to do it, and which means when I read these programs and I see like 20 people doing it exactly the same way, I will have some question marks in my head, because there are really so many ways of doing the same thing when it comes to this particular instruction set. With a pure RISC processor, the number of ways to combine things would be more limited, because each instruction can only do this much. But with a CISC instruction set, you can do it in many, many different ways. All right, so we're almost done. It's just one more statement to translate into assembly. How do you think we should do this one? Let's do with the right-hand side first. Okay, the right-hand side is really easy, right? You just move p node EBP to EAX. Now, how do I know that I should use EBP inside the parentheses?
Oh, because you already have it.
Because p node is a parameter, and with any parameter, it is only relative to EBP. Okay. What do we do next? We want to store that to whatever p list points to. Okay. So how do we? Okay. Now we know the p.
Just go to p node.
We already got it.
Yeah, we do.
It's already in EAX.
It's already in EAX, but I'm just not. I'm not going to optimize the program, so I'm going to redo everything here. Now we know that we need p list as a parameter, so we'll put it into EAX first, and well, put it into EDX. EDX is p list. What do we do next? Okay, hold on. Okay, let me give you an incorrect solution, and you tell me why this is not right. Okay, so what is wrong with doing something like this? Okay, what is being changed with this instruction? Let me turn on the line number so I can address the program in line numbers. At this point on line 23, what is getting changed? Where is that thing?
It's it's where plist is on the stack.
The parameter itself is getting changed. Okay, was that the intent of the code on line 21, the commented code? Line 21 wants to change not plist, but whatever plist points to. And yet on line 23, we are now changing just the parameter itself and not what it points to. So what we really want to do is kind of something like this, but we cannot do that instruction like this. We want to do another indirection like that, but we cannot, do it like this. So what is the option? Bring it into a register first, because we can only do the indirect on registers. So we want to put plist into edx, anything other than eax that we don't have to save and restore. Then the next step is going to copy eax, which is the right-hand side of the assignment, to whatever edx points to, because edx is plist. So now we are store the right-hand side to that. Are there any questions about how line 21 in C code is translated into line 22 to line 24 in assembly code? It's all about pointers and dereferencing. Let's go ahead and try this program and make sure that it works. Ooh, okay. Insert node. I forgot to do a global.
Yeah.
Oh, okay.
Yeah, the make file you never made
I have to refer to insert node to list. XS. Q. Now, the first time you run something like this, you may not want to put a breakpoint on line 36. Instead, you might want to put a breakpoint on line 32, assuming that you kept a little log of how the C code works. You should be able to follow the code and see whether the assembly code is doing the same thing as the C code or not. That is a really important step. I'm just trying to be brave here and put a breakpoint on line 36. Run the program. It didn't crash, which is good. Print whatever list points to. It has a value of 11, but that's not the end of it, because if I missed one of the steps, it is possible that it is pointing either back to itself or whatever plist is pointing to is not a valid location. So I have to verify that by printing the dereference of whatever list, the p next field of whatever list points to. I want to dereference that as well, and this is consistent with the C code. The result of the C code is consistent with this. So the program is working just fine. Okay. There's one last thing, because this is one thing that this program didn't have to do, but I do want to show you how it is going to be implemented in assembly. So vi list.c. Let's say here. Okay, let's think about this line here. How am I going to implement this insert node to list in assembly? Just this call here. Okay, we have to push the two parameters. Okay, we have to push the second parameter first, and that's the easy one. So we say push L, and then Pn is a local variable, and local variables, just like parameters, are relative to EBP. So assuming EBP is set up correctly, that will set up the second parameter. Are we okay with this? What about the first one? Well, let's see. If I do something like this, what am I pushing on the stack? I'm pushing list itself on the stack. What is the C code asking for?
The address.
The address. Okay, so we can't really do it this way. How do we figure out the address of list, the parameter? Well, we know it's relative to which register? EBP. Okay. So if I push EBP on the stack, I'm close. Not exactly there, but I will be close to the address of list, wouldn't I? Okay, so let's push it on the stack, and whatever we have to do, whatever adjustment we have to do, we can always do something like this, and just do it to whatever we just push on the stack. Is that making any sense? I just push EBP on the stack, and now I just want to do some minor adjustments to it so that it becomes the address of list. What should I do here so that whatever I just push on the stack is now adjusted to be the address of list? How about something like that? Because in assembly code, the name of a local variable or a parameter is the displacement from where EBP points to that construct. So if I add this displacement to EBP, which is just what I push on the stack, I will get the address of list. Okay? And that's it. That's how you take the address of something, and then you call insert node to list. When it returns, you just have to undo the 8 bytes. So you say add L $8 to ESP, because those 8 bytes are no longer useful to to this program, and that'll be the end of it. I don't have any way to verify this code is what is needed, but I'm pretty sure that it is the correct one. Yep.
If you have 3 or more nodes, how do you find the third or fourth or fifth node? Because what I saw is star, P node, and then the arrow next. That's to get the next item. But then what is the next of that?
Then you keep going. Okay, I can see what the question is. So we'll go ahead and do a few more steps. Okay, you're talking about something like this, and how do we track all the way down the list, right?
In GDB.
In GDB, very good. Okay, this is going to be fun. Okay. Okay, I'm being brave here. Put a breakpoint at the very end. Okay, and well, sometimes it's brave, and other times it's stupid. It's just plain stupid to skip everything and assume the program is working correctly. But I'm going to make that assumption here, because the point is to illustrate how do we follow this list, right? Okay, first, we can say, what is list? It has a value of 41. Does it make sense? It's the very last node that we add to the list. And remember, this behaves like a stack. So the last item that we add to it is the first item that we have access to. Next one is 17. That makes sense too. The next one is 11. Does it make sense? And the next one is 23, which is the last item, because the next one is a null pointer, which indicates this is the very last item of the list. Yep. So that's how you can track down a list like this. Okay. Any other questions about how a linked list works? Yep.
Yeah, we'll do the next one.
Well, we can do it. Okay. It will just give you a segmentation fault, or it will just cannot access a location 0 because you're trying to dereference a null pointer.
Can we do the next one?
It will give you the same message because it gets stuck at that point already. Oh, okay, it does something different. Cannot access memory at why would it be
0x?
But it doesn't make any sense because it should have it should have stopped at the it should have stopped here. So I don't know why it's complaining about 0x4.
That's a head scratch. Do the next one. I
Sorry?
have no idea.
Because I cannot dereference location 0.
No one can. No pay. You can't dereference any.
No, the IP next is 4 away from the beginning, so it doesn't care what it's at 0.
Right.
No, the first one. Yeah, we're more and more.
I know why it's dereferencing location 4. because that's the member. That's where the member is located relative to the structured address itself. So that's why it's complaining about 4 and not 0. Very good. Excellent. Excellent deduction.
One more go.
All right. So is this entire process, okay? I mean, does everybody understand this entire process? Everything from the beginning all the way to the debugging and the implementation part.
Homework's due on Tuesday or Thursday?
What is our last class?
It's Tuesday the following week.
Okay, so we'll make the due date.
No, it's Tuesday next week, excuse
So
me.
still, we have 2 more classes then.
Yeah.
Okay.
Because
We
they
have
start
2 more
finals halfway through
classes.
next week.
If I want to be bad, I will make the due date next Thursday.
Final
fine.
Thursday?
No. Our final is actually 2 weeks from today.
Oh, we skipped Thursday.
But they start finals halfway through next week,
don't
so
have a
Right.
Thursday class.
you have no classes after Wednesday of next week other than finals.
That's complicated.
This is online.
It's complicated, yes.
Tuesdays out for deadline.
It's complicated.
We have to ask Tuesday.
Okay, so what that means is, on next Tuesday we will have a review of the exam. If I'm gonna give you guys multiple choice, I can only talk about the topics, but I cannot really show you the sample questions, because it's pretty hard to show you the sample questions and be able to ask you the actual questions in the actual exam with a multiple choice test. But we will cover the material, regardless. So I have 1 week to decide how I want to structure the final exam.
Same way as the test. Same way as the test.
Same way as all the tests. Multiple choice.
Names.
The first multiple choice question is to give you like 40 names, names of all students in the class, and say, what is your name?
Yes. What's the professor's name? That way you can try this one.
Oh, which one is his last name? Tag? Hongyo? LosRios.edu.
What's your real last name? Tate? That's the question?
Question? Can you go up a little bit? Okay, let me stop again.